So what we did was we talked about what does a free body diagram look like. We finished up our forces. So we talked about gravity, friction. We talked about normal force, which is the force pushing up. I said the interesting thing about this is it's perpendicular to the force, to the surface, whereas friction is parallel to the surface. If you look at this thing here, parallel to the surface. So then what we did is after we did that, we talked about the next two forces, compression, which is when something gets squashed. And then we talked about tension. The tension force is when something gets pulled in either direction. In this case, the wire here is getting pulled down from the top and pulled up by the crane. We talked about net force. If there's no net force, there's nothing to draw. You've got an object in the ground. We've got gravity acting as a net force. You can have pushing forces. And then what we did was we had falling forces. We talked about the difference between balanced and unbalanced force. Balanced force means you've got a net force of 0. If you've got a non-balanced force, in this case, which is all of these, so in this case, the top and the bottom force is a net force of 0, they're balanced, but the left force is not balanced. So these are free body diagrams. And then we wrapped up in the end, and literally was the last 5 minutes, and I don't blame you guys if you missed it. What we did was we talked about how these forces can be drawn like this, and so therefore the overall force, which was calculated as being this big force along this diagonal, and we found out that we went 5 squared plus 4 squared, which I think we got the answer of being about 6.4, I think it was, but I can't remember exactly. This is what we're going to be working on today, so I'm going to give you guys a second to copy this down. Lesson 60, we will be able to calculate the net force made up of angles. So yeah, that's actually a really bad goal. But the idea is like, I want to explore a little bit more of these angles, the angle forces that we've been talking about. And I'm going to do one big question for you guys today. And then I'm going to give you guys the rest of the time, which should be, once I've finished, about 25 minutes to work on 10.2. Okay. We'll be able to calculate the net force made up of angle, which should be made up of angled forces. That'd be much better. Now what we're going to do is we're going to do 2 examples. One of the examples is a worded example that I wanted to do last lesson. The other example is going to be a there's going to be an angled example that I'm going to go through with you. I'm actually going to do it on the paper, and then once we've done that, I'll give you guys some time to work on 10.2. So let's move on. Let's get it done quickly, and so that we can have more time to work on 10.2. This is the question here. A mother is running with the pram. She pushes down on the pram at an angle of 40 degrees from the horizontal with 20 newtons of force. Okay. The pram experiences a frictional force of 8 newtons. What is the net force in the x direction? What is the net force in the y direction? I'm going to give you guys a second too. What I want you to do is, you don't have to copy this text down if you don't want to. What I would like you to do is, I'd like you to try, I'm going to give you guys about a minute to do this. I'd like you to try and draw this as an image. So I want you to try and take the information that's being given here and draw an image of it. What would it look like? Let's see, go for a minute from about now, and then I'm going to start working on the question on the paper. All right. I'm going to start getting ready to do this question on the paper. Again, unfortunately, you won't be able to see the question while I do it, which is why I gave you guys a chance to draw it. I can see it because, well, I'm the one that's running the show, but yeah. So I'm going to move this here. I'm going to move this here. I'm going to straighten this up a little bit. All right. So there are a couple of ways you could draw this. The mother is playing with the pram and she pushes down the pram. I realized that there are two ways that you could draw this image. Let's draw the pram. Pram is going to look like this. All things in physics just look like a box. Now there are two ways you could draw this. And I'm going to be honest with you guys, I haven't actually read the textbook enough to know which way is the right way to do it. But I'm going to show you both of them. The first way you could do it is you could say this. The mother is pushing down on the pram at an angle of 30 degrees from the horizontal. So here is a horizontal line. Here is 30 degrees. And that force is 8 newtons. Now the other, and then you've got a frictional force, which is going to be pushing against the direction. It's going to be pushing this way. That's a frictional force of 8 newtons. No, sorry, that's 20 newtons she's pushing down. It's 8 newtons here. Now, I think the better way to do it would be to actually draw it like this on the right. But it doesn't really matter as long as you understand the maths of what's going on here. We've got an angle, the pram is being pushed down. So therefore it's going to experience a force like this, getting pushed down into the ground. The frictional force is going to be against the motion. Now the reason that I like this one a bit more is because it's got all the vectors coming out of the center of origin, not going into it, which makes it a bit confusing which way the vectors are going. So we can actually sort of see, all right, we can sort of see the resultant vector is going to be somewhere around here. That's what F net would be. It would be somewhere around there. Where exactly and what angle, I'm not sure. This angle here is going to be 30 degrees. And you might say, well, how do you know it's 30 degrees? Because I can tell, because it's going to be, I can use that same logic of, what's it called? Geometry. It's a geometric thing, but it doesn't matter. 30 degrees from the horizontal. This is 8 newtons. This is 20 newtons. Now, the first thing it asks us is what is the force in the x direction? The x direction being the left to right. Okay, so the net force in the net force in x, the sum of the forces in the x direction are going to be, let's take, we're going to have -8. You might say, why did I say -8? Because I'm just going to say, well, I'm going to make this way positive. That's why I chose -8. Doesn't matter, whatever. And then I'm going to have plus, in the positive direction, I've got this 20 newtons. But that 20 newtons is not 20 newtons. It's not going to be plus 20 because it's an angle. So I've got to work out how much of this 20 newtons is going to the right. And the best way to do that is to say, well, how much of this is going to the right? Well, that's going to be a component of the triangle with 30 degrees, 20 newtons being at the hypotenuse. That is on the adjacent side. So that means it's going to be 20 newtons times cosine. Actually, it's not 30 degrees, it's 40 degrees from the horizontal. Shit. Sorry, guys. Cosine 40. Okay. Now, if that was a bit too quick for you guys, that jump there, let me know and I can go back over it later on. But what I've essentially done is I've said, well, this is a right angle triangle, therefore adjacent over hypotenuse gives me cosine. If I want to know this angle, I'm going to go 20 times cosine 40. That's going to be -8 plus plus -8, put this here, plus 20 times cosine 40 gives me 7.3. I'm actually just going to skip this step completely. 7.3, yeah, we'll just leave it as 2 decimal places. 7.3 newtons, and then because it's positive, I can say 7.3 newtons to the right. You can just leave it and put a positive sign here. I'm just going to write to the right just because I'm going to keep it going. It actually doesn't even say in this question which way you're pushing it, if you're pushing the pram forwards or backwards. So you could write 7.3 newtons forward. I think that, you know, wouldn't matter too much. Now, and in fact, if it was just a worded question like this, they probably either they would have to give you a picture, or they'd have to say, and this is actually my fault for writing a bad question. I probably should have said, yeah, the mother was pushing at a 30-degree, pushing the pram to the right. But, you know, I was in a hurry when I wrote this question. So, okay, as for the y, now the net force in the y direction, remember this sign here means net force, the net force or the sum of the forces. You could write F net, but I'm used to write the sum of the force in the y direction. Well, there's no force in the y direction that we talked about. Obviously, in this question, there would be gravity, there would be the normal force. We're ignoring that because we're just looking at what forces they've told us about. They've only told us about this one here. So the other one, if that is cosine, this down here, that's going to be sine because it's opposite. So therefore, f of y is going to be 20 sine 40. That's going to be 20 sine 40 is going to be 12.8. We'll go with 12.9. 12.9 newtons down. And that's it. So now we've got our force in the x direction and force in the y direction. We could then find, if we wanted to, the net force. So the net force is going to be the size of the net force. Sorry, let's do that. The size of the net force, I got the square root of 7.3 squared plus 12.9 squared. $14.8 newtons, and that's the size of the net force. I'm not going to actually calculate the angle. It would probably be a greater angle down, but I'm not going to calculate that because usually the questions don't actually ask you to do that. All right, are there any questions on what I've done here? Throw them in chat, say them out loud. You've only got a couple of seconds to let me know. If I went too quickly with this and you don't want me to talk about what you didn't get, I can go over it later. But yeah, that's how we do it, and that's why I spent so much time at the start dealing with vectors, so that I don't have to go back, hold your hand. Why did you flip it? Okay, so the reason that I flipped it is because I was looking at, when you do free body diagrams, you usually do free body diagrams as all of the forces coming away from the center. So it's like, if I have a block and I'm pushing down on that block, like I'm squashing that block into the table, instead of drawing it as being the block being pushed down into the table, what we actually draw is we usually draw the block and a force coming down out of that block downwards, because that's what's happening. The block is being forced down. Same with the idea with this pram. This pram is being forced down and to the right, okay? Because the person's pushing downwards. That's why I flipped it like that. Is because it's easier to draw it. And it also gives me an idea of where the possible vectors could be. because I know that it's not going to be up and to the right, because that would make sense. It gives you a better idea of where the net force is going to be, and it gives you a better idea of how to, attach those forces to each other. Then, cool. Any other questions? Good
Wait,
question.
sir, can you double check the 20 cos 40? Because I don't know why when I calculated it's like negative something.
Which one?
20 cos 40.
This one here.
Yeah, I don't know why it's, when I try it on like the calculator, I got negative 21.
Okay. 20
Hey,
cos.
you know what? Maybe because of your gradient thing, the gradient in the methods, Kevin.
Oh, okay.
Cos 40, I got 15.3. Yeah, if you're, but you got to make sure that you're stuck to degrees here. If you're not on degrees, if you've not got a D there, then you might have an issue. Isn't there no direction? So someone else says there's no direction component of the net force. Yeah, there is a direction component to the net force vector. I just didn't calculate it. I could have calculated it pretty easily by just going inverse tan of the opposite, which is going to be, in this case, the net force is going to be, so it's going to be down and to the right. So it's going to be down here somewhere. So therefore, I'm going to go opposite over adjacent, which is going to be, opposite is 12.9 over 7.3. Inverse tan of 12.9 over 7.3, which is going to give me, as I said, I looked it through some questions and I didn't actually see many where they actually got you to calculate it. Usually they'll get you to calculate the magnitude or size. So if you find the size, you don't need to do it. 60.4 degrees. 60.5 degrees, well, negative 60.5 degrees from the horizontal. Isn't there a no direction component of the net force vector? There is. It's not just, so someone's, it's not just negative 40. The reason it's not negative 40 is because when you subtract 8 newtons, it changes its vector. It actually makes this angle larger. And also, as I said, if you calculate just the size of the net force, you don't need to worry about it. Now I've got one more question. Is there anything else? By the way, this has been good. I really like you guys giving me answers here. Give me things. But if not, I'm going to jump all ahead. Last little thing I want to talk to you guys about before I let you guys work on 10.2 is I just wanted to show you guys this question here. So this question here, this is just a worked example question, but I thought I would show you guys a worded question, just because I gave this question as well before. A soccer ball is kicked along the grass and it slowly comes to a stop. Draw the free body diagram of the ball as it's rolling along the grass. So if I've got a ball, I'm going to represent the ball as a point, and it's kicked along the grass and it slowly comes to a stop. What forces, can you guys tell me what forces are acting on this ball as it's rolling along the grass? Someone's hit me up. We've got gravity. Great. First one we've got is we've got gravity. Pretend that's going straight down. What else have we got? The normal force. Thank you, Kelvin. With the normal force acting upwards. Those two are balanced. We know they're balanced because the ball is not sinking into the ground and it's not flying into the air. What's the other force acting as the ball slowly comes to a stop? Friction. Perfect. Now, friction could be this way here. We'll just do F and we'll do an FR. Now, even though that's the case, I do want to do one last thing here. I'm going to do in green. Now, this wouldn't actually, I'm actually not going to do it here. I'm just going to write here, I'm going to do an arrow. I'm going to write the motion of the object. So even though the force acting on it is to the right, the ball is going to be moving, even though the frictional force acting on the left, the ball is going to be moving to the right because it's slowing down. That's how we know this frictional force is slowly eating away at that motion, so it eventually stops. So being able to just draw a body here, a lot of the times when I get people to do this, they go, "Oh, I was kicked." So they go and they draw. The force. Where's my pen? I lost my pen. They go and they draw this, and they say, "Oh yeah, here's the kick. Here's the forward force. This is the forward force of it being kicked." And I'm like, no, because after it's kicked, after it leaves your foot, there is no more forward force anymore. And then that's the thing, is like as the ball is rolling along the grass, there is no forward force. All the force, the speed, the acceleration it got was from where it was first kicked. It slowly gets slowed down. So that's how you do. That's just a basic worded question. I saw a bunch of these on style when I gave that to my year 10 class. So I thought it was like, I'm going to give you guys a chance to have a look at them. Are there any questions about what I did with this question here? Now, if you had done this flipped over, that would have been fine. If you had the motion going to the left and the frictional force going the other way, it doesn't matter. I just chose the ball to be rolling to the right. It doesn't even say in the question which way the ball is kicked, so I don't need to worry about it. Now, I'm going to give you guys the rest of this lesson to work on 10.2.